Hey, what's going on, guys? Today I got a little project I'm running through with you guys. I installed a sub panel here in my garage. Not an electrician, not licensed to do this, but pretty detail oriented. We also got a city inspection coming up, so I want to try and get as much of that on camera as I can. So I'm trying to make this like something of a ultimate beginner's guide. You know, you have your panel in your garage, and you want to add some power in here, a couple extra outlets. Maybe you're looking to run an EV charging outlet, something like that. So I'm going to try and keep this as basic as possible. So let's start right here in the main panel, and then we'll run through everything from there. All right, guys. So if you've never seen one of these, this is the inside of a main breaker panel in a house. What we've got coming in right up here. Actually, before I even start, I want to kind of clear up a slight misconception. And some people think that when you flip off this main breaker right here at the top, it's kind of like a free-for-all in there, like it's a dead panel. And that is actually not the truth. Because if we think about this, all we've done by shutting this breaker off is de-electrify everything below this, right? So if we take a look at all these individual circuit branch breakers, we can use our non-voltage circuit detector, and we can see that they are indeed dead, right? Because we flipped the main breaker, so we've cut off the flow of electricity to each of these, but we haven't cut off the feed from the utility, and we can see right here that these are still definitely live. So be very careful. So that's what I got to work with. So just be careful when you're in here, and all you have to do is turn off the main breaker, because you will still have these live up here. So what we've got coming in on the left and right are two hots. Basically, these are 120 volts each out of phase. So between the two is 240 volts, which is why we get 240 volts when we tap each phase on a 2-pole breaker. Whereas individual 120 amp circuits like these are all the electrical and lighting circuits in the house. These are 120 volts to ground or neutral. And the bigger circuits in the house, I think this one is the range, I think this one is the dryer, 40 and 30 amps at 240 volts, because we're actually grabbing both phases, about 120 volts out of phase from each other. The center one here is our neutral, and this balances the load between the two. So when you hear about hots and neutrals, that is what they're referring to. We have coming in from the utility, 2 hots, 1 neutral. And you'll see over here, there's a green grounding screw. At the main service box here, the green grounding screw bonds the neutral and the ground. So basically we have here, this goes to, I think it's called a UFER. I can't remember what it stands for, but it's basically an electrode embedded in the foundation of my house. At the main panel here, they're grounded, or they're bonded, excuse me. And that's what this green screw here signifies. So whether return current in your house goes to the ground or goes through the neutral wire, they both ends up in the same place here at the main box. This is actually unbonded at the sub panel box. We'll get to that in a second. Here's my new circuit I've installed. It's a 60 amp breaker, so I'm feeding a 60 amp sub panel. And one thing to kind of keep in mind, and when you're planning all this, is breakers protect downstream wires. And why that little bit of information is important is because breakers are sized to the wires they are protecting. So we'll see each of these are each 20 amp breakers, and coming out of them are 12 amp or 12 gauge wire. And you can find that information, just look up American wire gauge amperage rating, and there's a bunch of NEC charts out there, National Electric Code, that explain or that match amperages to wire sizes. So in our 40 amp breaker right here, we have 8 gauge wire coming out. For our 30 amp breaker, which is going to our dryer, we have 10 gauge wire. Right here is our 60 amp breaker that leads to our sub panel. it's protecting 6-gauge wire. Now, if we actually look at that NEC chart that I talked about a few minutes ago, we'll find that 6-gauge wire is only rated to 55 amps, but there is an exception in the NEC that allows us to use the next standard size breaker up because nobody makes a 55 amp breaker. So the 60 amp breaker is permitted to protect 6-gauge wire. So we have our a hot again, hitting both of these phases of 120 volts. We have our neutral wire right here, which is providing the load balancing return. And we also have our ground right here. And really, because they're bonded, like this green screw up here shows us, it's really leading to the same spot. So that's about the tour of the main electrical panel here. But again, the key takeaway here is that we bond our neutral and our ground at the main panel only, and breakers are sized to the wire they are protecting. Okay, let's move on. All right, guys, so I'm just going to give you kind of a brief overview of what I did here. Right here, this is our 6.3 Romex or NM-B in-wall electrical service wire. It is run through bored holes in the studs, except at this corner here, which I couldn't really get to, so I notched it here using the 25% notching rule. And where the wire passes through the notch, I used nail plates because this is a code requirement, with the assumption being that in the future, someone might try and nail or screw in this area, and we don't want them nailing or screwing into a live electrical wire. This runs straight over through, again, some bored holes in the load-bearing studs right up to our sub panel. And this is, again, 6-gauge wire protected by a 60 amp breaker. From there, I've installed a 30 amp 240 volt only circuit, which you can kind of see here is signified by these 3 holes only. When you see a 4-hole 240 volt outlet, that means the appliance can pull both 120 and 240 volts from the circuit. This is a 30 amp circuit and it's protected by 10-gauge wire. I've also installed a dedicated 20 amp 120 volt circuit. Over here, running off camera, is a 8-gauge Romex wire, which is feeding a 40 amp circuit that will be used either for my welder or for an electric car I don't currently own. I haven't really decided what I'm going to use that one for yet. Right here, this is PVC conduit, 1/2 inch. Inside is 12-gauge individually stranded wire. So when you are running wire inside conduit, you do not run Romex or jacketed in-wall cable like this. You run individual conductors. And this is running out to my detached storage shed. That's the overview of what is happening in the sub-panel wiring. So let's open this up now, and we can take a look at what goes on inside this as opposed to what happens in the main panel. All right, so inside the sub-panel here, we've gone ahead and cut power at that 60 amp breaker, and we can verify that again using our non-contact voltage detector. You can see right here we are dealing with 2 dead circuits, so it's relatively safe to be in here right now. We have a 40 amp 2-pole breaker, which is bridging the 2 phases of 120 volt, and it is protecting 8-gauge wire. We have a 30 amp breaker that will be running a shop heater. Now you might see something different here. Hope you can see this on camera. Unlike the red and black wires we have that signify hot running out to our 40 amp circuit, we actually have a black and a white wire. That's because the cable used is 10-2. So in this cable, it is sort of wired for a hot and a neutral. And we're actually using this neutral wire as a hot. And to signify that we're doing that, we have to kind of mark it as such. So I've shrink wrapped some black on here to let whoever is in here in the future know that this, even though it is white and is traditionally a neutral colored wire, is actually a hot conductor. We also have our neutral here. So I showed you guys that green bonding screw in the main panel. In a sub panel, that would normally go right there, and this will come with your sub panel. And by the way, this is a Square D sub panel I purchased off Amazon. I'll place a link below. I like Square D stuff simply because, not because I think it's really better or worse than any other brand. It's just because it's available literally everywhere. You go to Home Depot, Lowe's, Ace, McClendon's here in Seattle. Everyone carries Square D breakers. It's sort of like the most common brand, at least in the Northwest that I've ever seen. You know, I'm sure Siemens or GE or Cutler Hammer are all just fine and work perfectly well, but I've noticed that their availability is a little more limited, so that's why I like these Square D panels. I also really like these Square D panels because in the most recent revisions of the National Electric Code, we are required to protect 120 volt circuits with both GFCI and AFCI breakers. Well, actually, you can do it with AFCI, GFCI outlets, but it's a lot easier to do it right here at the panel because then we can run our Romex ahead of it. So basically, that's why you see this kind of large looking breaker. This is a combination ground fault and arc fault interrupting breaker. So it's going to protect the circuit from any current flowing in the ground, which is basically telling the circuit that something might be malfunctioning in the attached equipment. And the arc fault function basically protects from like arcs in wire, or maybe a stripped wire coming in contact with another conductor or something like that. The downside to these is, even though they are very nice, they are very expensive. A normal, just non-GFCI, non-AFCI 20 amp Square D breaker would probably cost $4 or $5, where these AFCI, GFCI breakers cost about $50. So, it's a nice peace of mind to have, and it's required by the NEC, but they are expensive. So over here, a lot of times these panels do not come with ground bars, because the expectation is that they will be used as main panels, and this green grounding screw that is included that you're not going to use will be in place, thus bonding the ground and neutral. But because we don't do that, we have to add a separate ground bar, which is over here. And these sometimes they come in kits. Most of the time they have to be purchased separately. Okay, that's the overview of our sub panel box. Now I'm going to close things up, and I'm going to kind of flip the breaker back on and try and maybe run over how I test a few of these circuits and get an idea of whether things are wired correctly. All right, guys, so I've turned the power back on to the sub panel back at the main breaker, flipped the 60 amp breaker back on. So what I'm going to do now is use my multimeter and just kind of verify that we have the expected voltages and continuity to ground that we would expect to have. I know we talked about my separate non-contact voltage detector earlier. They're very handy and very cheap and allow us to very quickly verify whether a load is live or not. And you can see here, it is. However, if you purchase a multimeter like this unit, a lot of them have non-contact voltage detectors built in. I'll place a link to this one in the description below. It is very handy and only runs about $30. And we can see here, right up at the top, is a little thing that says NCV, non-contact voltage, and we can use it just like we used our little separate one and verify there that this is a live wire. So now if we turn it from non-contact voltage mode over to voltage detection, select AC, zero it out. We're going to use our probes here. And remember how we said before that on a 240 volt circuit, we are really just bridging to 120 volt circuits. So between what we should expect to see if we've done everything right is between these two hots, 240 volts. Between either of these hots and the ground, 120 volts. And between either of these two hots and even this metal casing, if it's properly bonded, which it should be, 120 volts. From our ground to our bonded enclosure, 0 volts. So let's see what we've got here. Turn my light on there, maybe. All right, so we can see there, we have 243 volts between our two hots. Between one hot and our ground, if we can get them in there. Sometimes these plugs are kind of big and it's kind of tough to find exactly where the contacts line up. There we go. Between our hot and our ground, 122 volts. Between our other hot and our ground, 122 volts. And to check whether this is properly bonded, what we can do is grab a hot and see if we get 120 volts to the enclosure. 122 volts. So I think we can safely say that this particular outlet is properly wired. 120 volt circuits are even easier. We can buy a circuit detector. Again, I'm not sure what these 100% are called, but they basically just plug into a 120 volt outlet, and with these 3 lights tell you whether it's properly wired. So let's plug that in. We see 2 oranges. Basically the left red is off. 2 oranges, and if we read the little key up top, you can see that. I don't think that'll be big enough to come on camera. We basically see nothing orange is correct. These also provide another function, and that is to verify the circuit is ground fault interrupted. So if we press this little test button on top, it's going to divert a little bit of that hot current into the ground and should flip the breaker. And so when we press this button, these 2 lights should turn off. And if you hear that, that was the breaker indeed detecting a ground fault and interrupting electrical flow to this outlet. And turn the circuit back on, and we see that we again have power to this. And this is probably a tool that the inspector is going to use. Okay, the next thing I want to show you is our conduit run out to our storage shed. It is 1/2 inch schedule 40 PVC conduit. If you've never run conduit before, I would highly recommend going PVC route. It is very forgiving, very easy to cut, and just generally a lot easier to use than EMT or metallic conduit. Also, if I'm being honest, this particular run of conduit is one of the things I'm slightly concerned about on the inspection, simply because if we were to notch this stud and run this PVC conduit through it, we would need a nail plate on the front, just like we have with our Romex cable over there. Well, this isn't notched into the stud, but it will be running relatively close to the finished drywall. So I couldn't figure out a good code reference to whether this needs some kind of metallic protector on it. Right now, it doesn't, obviously. And if the inspector doesn't call it out, I'm just gonna leave it as is. If he does, then I'll have to fabricate something. So let's go outside and I'll show you the rest of the run. All right, this is the trench that the 1/2 inch PVC conduit is buried in. Normally, PVC conduit needs to be buried deeper than this, but there is an exception in the NEC that allows for a reduced burial depth on PVC conduit carrying a single 20 amp or less circuit that is also GFCI protected, aka storage shed or outhouse circuits. So what that reduced depth is 6 inches to the top of the pipe, covered by 2 inches of poured concrete. And we can see here it's probably more like 3 inches of concrete. So the pipe itself, the top of the pipe is actually about 7 or 8 inches down, and then I've got 2 or 3 inches of concrete on top of it. And the basically idea behind that is that in the future, if somebody is out here with a shovel or something, they're not going to accidentally shove their shovel into a live wire. This is actually item number 2 that I'm slightly concerned about on the inspection. The other reason is I found conflicting information on the requirement of whether I need to lay electrical marking tape in here. Basically, it's like a red tape that just says electrical line or something like that on it. Some forums seem to indicate that it's required, others don't. So for now, I don't have any. And if the inspector calls it out, I'll go buy some. If not, then I'm just gonna rebury it. All right, guys, that is the conclusion of my sub panel installation. Just to recap, we have a 60 amp breaker in our main panel, protecting 6-gauge wire that runs over to this panel. In this panel, we have a 40 amp breaker protecting 8-gauge wire. We have a 30 amp breaker protecting 10-gauge wire. And we have 220 volt, 20 amp circuits, each protecting 12-gauge wire. The inspection I'm going to order today, so it might take place tomorrow or the next day, and I'll try and get as much of that on camera as I can. I don't know how comfortable an inspector is going to be with a camera on them, or if not, I might just kind of discreetly place the camera and get a wide angle overview for you guys. Hello.
How are you doing, sir?
Good. How are you?
Oh, just been busy.
Oh, busy. Okay.
Yeah, very good. I was gonna say you have it. It's a normal,
Oh yeah, I
understand. We are having that little room.
Yeah, so we have this sub panel here.
Okay.
So basically over here is our main panel, and
I see that one right there.
we have our new 60 amp. Yep.
Okay. Looks like the other side. I inspected your house.
Oh.
3-4 years ago.
Okay.
I try to remember, but yeah, I've been in Korea for like 21 years now, so I remember the houses and stuff. So from here, just go down to the other area. And which one is the one goes there? This one? Right?
Yes. So this is all new.
Yep. Yeah, no, I'm saying the one that goes to the
Oh, to the shed.
to the shed.
Yes, this conduit here.
Okay, let's take a quick peek at the shed.
Oh, she needs keys for the shed.
Okay, thanks. There's something here.
Yeah.
And that's the gate right there.
Yeah.
Now, seems like if you done this right, I'm sure you did you did the main one. That's the only scary one. Did for a homeowner, so did you turn off the main one to connect the other one? Or?
Yeah. Yes.
Yes, so because it's sometimes kind of scary for, some people that are, but, you look like you're good with your hands, so,
Thank you.
so everything works good. Okay, sir, that's about it, and you have a very nice day, and I'll see you on your next project.
Okay, thank you very much. I thought this was going to take longer.
Oh, no, I mean, everything is open, so I can see the wiring and the size of the wires and stuff, so.
Sure. So I'm good to drywall everything back up now?
Everything looks good.
Okay. Well,
Okay, you have a nice day.
thank you. You do the same. Wow. That was like super easy. So the inspection went as well as I could have hoped. No issues called out and completed in less than 10 minutes. Interestingly, he didn't seem all that interested in the 240 volt circuits or even the sub panel itself, outside of making sure the breakers were correctly sized for the wires they were protecting and that the circuits were individually labeled. The only place he opened anything up was out in the shed, where it's 120 volts only. Out there, he made sure a disconnecting switch did indeed cut power to the entire building, and that the GFCI function was operating as expected. Other than that, it was super low-key. I've read some forum horror stories about inspectors that would give Himmler a run for his money, but in my limited experience, those type are either the exception or I just got lucky. Overall, he came across as very professional. He didn't seem concerned with nitpicking the install, instead focusing on ensuring there weren't any major or obvious code violations. In any case, I can call this project done, and we'll see you next time.